Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 2, Lesson number 7 on more work with average rate of change. So calculus and the study of calculus is all about modeling how quickly a phenomenon changes. But when we model how fast something changes, implicitly what we're doing is we're modeling how fast it's changing compared to how fast something else is changing. Very often time. In other words, when we talk about something, an object moving at 65 miles per hour, what we're talking about is as time changes by 1 hour, the distance is changing by 65 miles. So our first attempt in actually doing this modeling is by using average rate of change. Let's start by reviewing the formula for average rate of change. All right. So average rate of change says for a function f of x defined over the interval a to b, the average rate of change is the following. All right. Now often formulas like this can be very, very abstract. So just for a moment, let's make sure that we kind of understand sort of the geometric idea of this. Let's say that we've got this graph grid and we've got some function, right, that travels over an interval a to b. Right, over a to b. Then clearly over the interval a to b there is some change in the independent variable, right? That can always be calculated by b minus a. There's also then a change, let me put all these dashed lines on. There's also obviously a change in the dependent variable, right? The function itself, we'll call that delta f. That's calculated by finding the function's value at the second endpoint, at the second endpoint, but we don't want an equals sign there, and subtracting the first one. So we get this classic formula, right? And what we're doing is just like we measure distance versus time, we'll measure the we'll measure the change in the function's value, delta f, compared to the change in the independent variable, delta x. Please make sure that you keep it in this order. Although it would work fine to do this calculation, all right, what that would really imply is that we were moving in this direction along the x-axis, and we don't want to do that. Although it does give the same calculation, it's really not the way you want to think about it. Keep that independent variable increasing, make sure this increases, and then see how the dependent variable, the y value, the function's value, changes by comparison. All right, I'm going to clear this out, and then we're going to start to do some problems, okay? All right, here we go. So let's jump into it. Exercise 1, very simple. I'm going to give you the simple quadratic function f of x equals x squared, and we want to calculate the average rate of change over the following intervals. Now remember, these intervals, right? These intervals are always domain intervals. They're always intervals of x, right? So, we can kind of blindly apply the formula f of 2 minus f of 0 divided by 2 minus 0. And this is pretty easy. F of 2 squared is 4. F of 0 is 0. 2 minus 0. And we get 2. So the average rate of change is 2. All right, big deal. Why don't you pause the video now and calculate the average rate of change in letter B and letter C. All right, let's go through it. So again, just, kind of blindly applying the formula, I want to find the change in f, which I'll get by f of 4 minus f of 2, divided by 4 minus 2. F of 4 is 16, f of 2 is 4, divided by 2. That gives me 12 divided by 2, that gives me 6. I'm going to have to write a little bit smaller here for letter C. F of 6 minus f of 4 divided by 6 minus 4. 36 minus 16 divided by 2 gives me 20 divided by 2 and gives me 10. Now letter D says, illustrate below with a sketch the graphical interpretations of the three values you found in A through C. What appears to be true about the average rate of change as x grows larger, that is, at least for x greater than 0. All right, so let's illustrate this. Now what I'm going to do is I'm only going to draw the portion of the parabola that's in this quadrant, that's in the first quadrant. right? The reason that I'm going to do that is that I'm not really looking at the average rate of change anywhere else, okay? So let me just 1, 2, 3, 4, 5, 6, right? And again, the idea is in this first calculation, let me do this in, let's say, red, okay? Really, what I did is I took the point at 0, 0, all right, and the point at 2, 4, and what I really did was I just found the slope of that line, right? So the slope of that line was 2. Sorry about the poor scale on the axis here. Then what I did was in this calculation, right, I took the point at 2, 4, which is now here, and the point that was at 4, 16, which is now here, and I found the slope of this line. And that was m equals 6. And finally, let me go, I'll go in black, right? Then I took the point right here, and the point at 6, 36, and I calculated the slope of this line. All right, and that was m equals 10. Now I think it's probably clearly obvious, right, that the average rate of change is getting larger. The average rate of change is getting larger. Now the real question is, why is that? And that's because the curve itself is getting steeper, right? And again, what we're doing here, it's not so much about these secant lines. Those are what those 3 lines are called. It's not about the secant lines. What it's really about is measuring how quickly, on average, the output on this parabola is changing as the input changes. Because the function that we're dealing with is not linear, i.e. the graph of it is not a line, what's happening is that that average rate of change is changing. Okay? So pause the video now and write down anything you need to. All right, here we go. I'm going to clear it out. Okay. Now, exercise number 2. It's pretty straightforward. It says for a particular function f of x, it is known that the average rate of change over the interval 3 to 7 is negative 2. If f of 3 is 16, what is the value of f of 7? I'd like you to work on this problem a little bit. And then when we come back, I'm going to show you 2 different ways to think about it, okay? All right, let's talk about it. Now, in my experience, the vast majority of students who do this problem, I'm going to just draw a little dividing line here so I can do one approach over here and one approach over here. The vast majority of students who work on this problem do it the same way, all right? And they do it in a great way. They say, all right, I know that f of 7 minus f of 3 over 7 minus 3 is equal to negative 2, right? The average rate of change is equal to negative 2. Now, I don't know what f of 7 is, but I know that f of 3 is equal to 16. And of course, I know that 7 minus 4 is 3. And then they just solve. You know, sometimes they'll use an x here, which is, I guess, okay, a little bit weird. But then I'll get f of 7 minus 16 is equal to negative 6. And then add 16 to both sides, and I'll find f of 7 is 10. Why doesn't that seem right? Oh, I know I'm doing something wrong, primarily because I'm not getting the right answer. Sorry, I botched that. That's 7 minus 3, not 7 minus 4, and now everything is gone awry. I got to get rid of that, and that, and that, that, and that, All right, let's take it from not the top, but that should be 7 minus 3, which is 4. This should be a 4. There should be a 4 here. This should be a negative 8. Whew, and f of 7 is 8. Sorry, my apologies there. I was getting ahead of myself. Oftentimes I'll see something like 7 minus 3, and I'll work out the answer in my head, and it's a 4, and then the 4 just goes somewhere randomly. Sorry about that. All right, so f of 7 is 8. And that's great, and there's nothing wrong with doing it that way. But an idea that's very important is something that you could have easily missed out on over time. So let's talk about this idea. The average rate of change, I'm going to abbreviate it like this. It has nothing to do with arcs. The average rate of change is delta f over delta x, right? Now, if I multiply both sides of this equation by delta x, right, then what I see is I see that the change in the function can always be calculated by taking the average rate of change and multiplying it by delta x. All right, just think about that for a minute. All right, how much the function has changed is equal to the average rate of change times delta x. You all understand this perfectly well, right? If I have a car that's moving on average 65 miles per hour, right? And let's say I have a change in time of 2 hours, then I find a change in distance, if you will, of 130 miles. It's exactly the same idea here, okay? Exactly the same idea. If I want to know how much a function has changed, right, then I just take the average rate of change and I multiply it by how much the output has changed. But keep in mind, of course, that the delta f is f of b minus f of a. So that's the average rate of change times delta x. And this is kind of cool. Watch this. Now you might be saying, come on, I got the answer right doing it the other way. Why do I have to think about this? It's important. I wouldn't be pointing it out if it wouldn't pay dividends later on, okay, aside from this problem. If I want to know the y value on a function, right, if I know the y value at one particular x value, and I want to know the y value somewhere else, then all I need to know is the average rate of change and how much x has changed. So if I want to know what f of 7 is, that's just f of 3 plus the average rate of change times delta x. If I know the y value I begin at, which is 16, I know how fast I'm changing, which is negative 2 units of y for 1 unit of x, and I know how much x has changed, which is 4, then that will give me my final y value. All right? If you know where you start in terms of your y value, and you know how fast you're moving, so to speak, then you can find out where you end up. Okay? So we're going to see this on and off throughout the year, and you'll see it a lot next year when you look at what's known as integral calculus. All right, well, pause the video now and write down anything you need to before we go on to the next problem. All right, I'm going to clear out the text. There we go. Let's take a look at a next one that's kind of neat. It says, given the function h of x equals 5x minus 7, find the average rate of change over a variety of different intervals. Some of these intervals are very sort of, solid, regular, right? And some of them are more abstract, like these two, okay? Now, most certainly, you can do A and B. You might even be able to do A, B, C, D, and E, okay? But what I'd like you to do now is pause the video and work on A and B at least. And if you feel like you can do C and D and E after all is said and done, go ahead and do it. But we'll probably pause the video again at some point. All right, let's go through A and B. No problem, right? We just blindly apply the formula. H of 4 minus h of 0 divided by 4 minus 0. I'm going to just do the calculations here. H of 4 would be 5 times 4 is 20, minus 7 would be 13. H of 0, got to be careful there, is negative 7. And of course, 4 minus 0 is 4. 13 plus 7 is 20, divided by 4 gives me an average rate of change of 5. All right, whatever, let's do this one. H of 3 minus H of negative 2 divided by 3 minus, again, watch out, 3 minus negative 2. Let's see, H of 3, 5 times 3 is 15, minus 7 is 8, minus H of negative 2, 5 times negative 2 is negative 10, minus 7 is negative 17, right? And 3 plus 2 is 5. So I'll get 25 divided by 5, and that gives me 5. That's a little weird that we got the average rate of change being the same in those two. Now, I wonder why that is. Maybe it's always the same. Maybe it's not. Well, one way to see whether it's always the same or not is to not specify the two values. Let's figure out the average rate of change as we go from A to B. This is cool, right? There's absolutely no reason why we can't do this. So we just kind of blindly put it in. Now, H of B, that'll be 5B minus 7. No problem. We have to watch out for H of A because although it's easy, it's 5A minus 7. It's absolutely critical that we have these parentheses. All right, if not, we're not going to be subtracting a negative 7. We're going to be subtracting a 7. So what do I get? I get 5B minus 7 minus 5A plus 7, all divided by B minus A. Notice the 7's now cancel. I have 5B minus 5A divided by B minus A. That's 5 times B minus A, quantity, divided by B minus A. Those cancel, and I get 5. And that's super cool, because without even doing letter D, we just figured out that no matter what beginning and ending point we start with on this function, the average rate of change is always 5. So let's do it for letter D, and then we'll talk about letter E. All right. Here I'll have f of x plus h minus f of x all over x plus h minus h. F of x plus h is going to be 5 times x plus h minus 7 minus f of x. Again, be careful with the parentheses use. Got to have parentheses around that. And of course here the x is, whoops, I don't know why I did that. Should have been an h, that should have been an x. Here the x's cancel, and we're just left with that. In fact, one could say that the delta x here just is h. Now let's keep going. We get 5x plus 5h minus 7 minus 5x plus 7 all over h. Cancel, 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 cancel. And we get 5h divided by h, cancel, and we get 5. Again, independent of the beginning and the ending point. So letter E asks us, what is the average rate? It should say why, it shouldn't say what. Bad English, bad. Why is the average rate of change independent of the interval in this problem? So it didn't matter, it was 5, 5, 5, 5, 5. Why is that? Think about it for a moment. All right. Well, it's independent because this is a linear function and linear functions have constant slopes. Right, that's it. So you can give me any interval you want, messy or nice, and my average rate of change formula is going to always come out to 5 because that's the slope of this linear function. Right? And that's important. What makes a linear function is that its average rate of change is always the same no matter what 2 points you pick. What makes things nonlinear is that the average rate of change changes. All right. Pause the video now and copy down anything you need to. All right, I'm going to clear out the text. And let's keep moving on. Okay, here comes a really nice applied problem. All right, now we're going to use our calculators for that, and we'll bring them out in a second. But let's just get used to the problem. It says chemists are able to model the Celsius temperature of a reaction as the function of the number of minutes t since it started for 0 less than or equal to t less than or equal to 15 by this equation. Now again, before we get into any average rate of change, again, make sure that you always understand applied equations, right? C of t gives us the Celsius temperature. All right. T, on the other hand, gives us the time in minutes. All right. Now, letter A asks us to calculate an average rate of change, letter B asks us to calculate an average rate of change, and they're going to get a little messy because of how messy the function is. This is where we can use function notation on the calculator to really make our lives easier. So what I'm going to do now is I'm going to bring out the TI-84 Plus. There it is. All right. And I'm going to show you how to do most of this just in the calculator. It's really quite nice. We've seen this before, but let's look at it again. All right. Hit the y equals button. Okay. I want you to clear out any equations that might be in y1, y2, etc. If there are any in there. Let's get those cleared out. All right. And now let's put this equation in. We're going to put it in terms of x, okay, not in terms of t, but that's okay. Depending on how old your calculator is, you have to be kind of careful with your parentheses use. So I'm going to be putting, parentheses, 25 x squared plus 200 times x plus 225 divided by parentheses x to the third, got to get out of that exponent now, plus 9 parentheses. All right, once I've got that function in there, I want to take a good hard look at it. I want to make sure I haven't botched anything. Okay, but it looks good. And now I'm going to get out of there. Okay, so what I want to do is I want to use function notation. Now, in order to justify my answer on this problem, all I'm going to write down is c of 2 minus c of 0 divided by 2 minus 0. All right, so watch as I calculate just the numerator very, very easily. All right, so here's what I'm going to do. Find that vars button. It's right over here. See it? So I'm going to hit vars. I'm going to go over to yvars. I'm going to go down to function, and I'm going to hit enter. And now I'm going to pick off y1. Okay. Let me pause for a minute, get you caught up. Now, we're out on the main screen now. So I'm going to put parentheses, 2, parentheses. Now I'm going to do it all over again. Minus vars, yvars, y1, hit enter. And now I'm going to put parentheses, 0, parentheses. And now enter. Now keep in mind what I did is I just evaluated the numerator. That's all I did. So that's like 17.647, etc. divided by 2. And now I can finish this off by just doing divided by 2, enter. And I've now got 8.824, and it says include appropriate units. This is very, very important. I want you to think about what the units are in this calculation. All right, I think most people can get it at this point, but it's very, very simple. You see, the numerator has units of degrees Celsius. The denominator has units of minutes, and those things never leave. The final units are 8.824, 3 decimal places of accuracy, 8.824 degrees Celsius per minute. All right. Why don't you go ahead and calculate the average rate of change in letter B? All right, let's go through it. Now again, all the justification I need is this statement. C4 minus C of 2 divided by 4 minus 2. All right, let's do it. Let's go into vars, yvars, function, and y1, parentheses 4, parentheses, minus vars, y vars, function 2. So I'm going to grab y1, and then I'm back out to the main screen, parentheses 2, parentheses. And I hit enter, and now I have negative 23.126, etc., divided by 2. That gives me negative 11.563 degrees Celsius per minute. All right, now letter C, very important. How do you interpret your answers you found in parts A and B? And the phrasing here has to be just so. So what I want to do is I want to pause the video and I want you to just mentally think about how you interpret them. If you feel confident, go ahead and write down what you would write down on a test, and then we'll talk about the technical language you should use. All right, let's go through it. I'm going to just label them as A and B. So in A, how do I interpret this? On the interval, very important, on the interval, 0 less than or equal to 2, less than or equal t less than or equal to 2, the temp is increasing. Again, important word. On average, also important, by 8.824 degrees Celsius per minute. All right. And boy, the second one has a very, very similar interpretation. We'll say on the interval, what do we have? 2 less than or equal to t less than or equal to 4. The temp is decreasing. Oh boy, that looks terrible. Decreasing on average. 11.563 degrees C per minute. All right. The three things I've underlined there are extremely important whenever you're interpreting average rate of change. The interval is very important because unless you're talking about a linear function, which this certainly isn't, the interval will dictate the average rate of change. Whether the output is increasing or decreasing, and of course that's just all due to whether or not the delta F is positive or negative. And then finally, the fact that it is either increasing or decreasing on an average. One of the biggest mistakes students would make here is just saying, well, the temperature is increasing by 8.824 degrees Celsius per minute. And that it's not doing, right? It's doing it on average, but it's not doing it at every moment in time. All right. Well, I'll pause the video now. I'm going to clear it out, and then we'll finish up. All right, here we go. Let's finish. So today, we worked more with the classic formula for average rate of change. Now, more important than knowing the formula is understanding what you're really doing. You're comparing, for a given change in the independent variable, how much the dependent variable, the function itself, changed compared to the independent variable. And we simply do that by a division, by a ratio, right? Ratio and rate, very similar terms, okay? And we want to be able to think about that in the context of just the graphical line whose slope we're determining, as well as some physical scenarios like what we had in the last problem. All right, well, we'll certainly work on this topic more in the coming lessons, months, etc. For now, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking.